In this video, I'm going to talk about some issues about significance testing that I wrote about in this document that has already been loaded to Canvas. But if any of these issues were confusing to you, then hearing me talk about it may clarify some things or refresh your memory. And so I'm going to hit on a couple of the more relevant parts in terms of understanding type 1 and type 2 error and the central limit theorem. And again, this serves as sort of a refresher to things that I've covered in class. First of all, going through here, one of the most important things to understand or recognize is that the shape of the curve that we're talking about here represents the probability at any given location in the curve of an individual's score appearing. So when we see these numbers here, the different percentages, these are the areas between the lines. This area here is 34.13% of the curve, while this area constitutes 13.59% of the curve. And these are scores, these are people. So if you were talking about, let's say, intelligence test scores, what we're saying is that this portion of the population in between these two marks is constituted by 13.59% of the people who have taken the test. This is a very convenient strategy for us to use in terms of representing an individual score, because if the person has a score right at the center, then we would say that that person has a z-score of 0, where 0 represents the number of standard deviation units above or below the curve. That is to say, this is the arithmetic mean of the population. Now, in this particular illustration that I got from a different textbook, they're using x bar, which represents the sample mean, but really we should think of this as the Greek letter mu, which represents the population mean. If a person had a score of 1 standard deviation below the mean, that would be the same as a z-score of -1. And so you see here on top the symbol -1 sigma, lowercase Greek letter sigma, and that represents 1 standard deviation below the mean. If it's an intelligence test score with a standard deviation of 15 and a mean of 100, this person's raw score right here would be 85. But another way to think about that is using z-scores. We can say that that person has a z-score of -1, and up here you have the formula for z-scores, where you have x minus the population mean divided by the population standard deviation. And then the other way to think about this is with the person's score in place, we can then identify the proportion of the curve that falls below. You would simply take this area and add it to this area, and that would be the total proportion of the curve that falls below a z-score of -1. So grabbing my calculator, I always have a calculator nearby, and I don't have this set up in advance. Grabbing my calculator, adding 13.59 to 2.15, I get the value of 15.74. That tells me that there's, from this point down, is 15.74% of the curve. And then if I wanted to find what proportion fell above this point, it would be 34.13 added to 50%, because we know that each half is going to have 50% of the curve. From here to here, if you follow the blue cursor, I enlarged it to make it easier to see, that's 50% of the curve. So we can therefore extrapolate the 34.13 plus 50%, which would be 84.13. That's the proportion, or percentage rather, that falls above this particular position right here on the curve. So that part is fairly easy to follow. And using these same principles, we can determine the area between any 2 points on the curve, or the area above or below any single point on the curve, which is essentially what intelligence testing is all about. And in school psychology, the idea is that we test children who may be eligible for services within the school district, and we use that information on the intelligence test in order to see if that person is in fact eligible based on criteria that are preset. Now there may be other criteria as well, but the intelligence test score is often used in relation to that. Now this next graph, what I have here for figure 4, this is one that I think what I did here is I took out the original shadings and I added my own shadings to represent the 2.5% at the very tail of the distribution. When we talk about a critical region, what we're talking about is the 5% of the curve that is in the extreme tails. 2.5% of that 5% is going to be on the top. 2.5% of that 5% is going to be underneath. In other words, what we do is we take that 5% and we divide it in half. Half of it going in the lower tail, half of it going in the upper tail. And as I relate in my classes in discussion, the history behind this is that Fisher, Ronald Fisher, in the I guess around the 1920s, he proposed that a good way to think about statistics in terms of whether something is sufficiently rare to think that there's something unusual going on with the numbers that you're working with. He proposed what he called the 5% rule, that if a test statistic is unlikely to have happened by accident, if it reaches that 5% threshold, then we can say that there's probably something worth looking at here, although he never said that it proved that the variable had the impact. He said that if it reached that 5% threshold, and this is the shaded region that we're looking at here, the 5% threshold of probability, then it probably merits a closer examination by the researcher. And of course, in Fisher's day, what he was looking at was agricultural products, specifically the place that he worked at the time was working on different types of fertilizer that would be used in agriculture, and that was really big business. It was a lot of money involved. It was one of the mainstays of the British economy of those days, and so having the correct amount of fertilizer to produce the best crop yield was a very important thing to know how to do. But not only that, in other areas where crops would be used, such as making beer. And so Gossett, one of the other statisticians who sort of aligned with Fisher and developed some of these techniques in the early part of the 20th century, Gossett was working at the Guinness Brewery and devised tests based on the same 5% rule. He devised the t-test, where you have the lower part of the distribution having 2.5%, and again the higher part having 2.5%. But Gossett's distribution was a series of distributions for the t-test, because every different degrees of freedom that you have based on sample size yields a somewhat different shape of curve. The curve that we see here is the one sort of universal probability curve when you have z-tests or z-scores. There's only a single curve that represents that probability distribution. But when you shift over to t-tests, then every different degree of freedom that you have, whether you, let's say you had an independent samples t-test with 20 people, 10 in each group of 2 groups, your degrees of freedom are going to be 18. That's going to have a different probability curve than if you had 22 degrees of freedom or 30 degrees of freedom or anything else. That's why when you look in the back of our stats textbook, you see the table that has the degrees of freedom aligned across rows, and you have to look up the specific degrees of freedom for the alpha value that you have. And alpha is almost always set at 0.05 or 5%, and that represents the shaded region at either side. The next point that I want to cover here is the relationship of confidence intervals to the central limit theorem. And so here you see the z confidence interval, And what this is useful for is if you're trying to understand, based on your sample, where the population mean might be. If you have the information to plug in here, then you can set it up like this, and the resulting interval tells you that based on the sample that you have, the population mean is going to be within that interval from here to here 95% of the time. Now this example that we're looking at on the screen right now is a little bit artificial, because if you knew the population mean, which is mu, I guess I can't highlight things on this PDF, right here, then we don't have to make an estimate of where it is. So this is a little bit theoretical and artificial. But it could be that we have a sample and we're trying to tell whether this sample is different than the population. Actually, what we ought to be using is a t confidence interval, but it works on the same principle. Now my point here is that if we are sampling from a population, and let's say that we know that the population mean is right here where this blue line is, every time we sample we're going to have some variation, even if we did not give any treatment to that sample. Now in this case, let's say that this sample mean is, or rather this population mean is set. We may even know what it is, but every time that we sample we're going to get something a little bit different based on random factors. And what this illustration that I created here shows us is that every time we have a sample mean, that sample mean designated by all these different little X bars is going to be different than the population mean. In fact, almost never will you have a sample that matches the original population mean. Even if you did not provide any treatment to that sample, the sample is almost never going to look exactly like the population mean. And the distance of this interval is a function of the sample size, so that as sample size gets larger, the interval here will get narrower and narrower. In other words, it'll become, I guess you could say, more accurate in terms of a representation of where that true population mean is. And that's why whenever you look at political polls about potential voters' preferences for presidential candidates or anyone else, when you look at public opinion polls, they invariably, at least if they're done professionally, they report the margin of error, or MOE, and that margin of error is the essentially the width of the confidence interval. You can think about it as. So if they say that the error, the MOE, is plus or minus 3 percentage points, and if you have an estimated 60% of people being in favor of candidate X, then it could be as high as 63% or as low as 57%. But probably, you know, what you're going to be looking at is most of the time that you sample, it's going to be fairly close to the true population mean, but there will be some variation. It's never going to be exact. So we're comfortable with having error in our measurements, or at least we should be, but we have to understand the limits that are placed on it. And in this formula, where I have the standard error, this is the x sigma sub x bar is the symbol for the standard error. This tells us how the sample functions, the sample size functions, to change the width of the confidence interval. As the sample size, in this case I have a sample size of 100, as the sample size increases, you're dividing a larger and larger number into the population standard deviation, which will in turn make the standard error much smaller. And so if I had 10,000 people instead of just 100, this number would become infinitesimally small, and what that would do in turn is make the range of the confidence interval perhaps from here to here, rather than what we see in this graphic, which is quite wide. The larger sample would give you a very tiny confidence interval. Okay, so keep that in mind, and what I want to do is I want to walk past some of this stuff. You can read that on your own, but I want to talk about the type 1 and type 2 error, because I know that this is something that can be confusing to to many students, and also to people who work professionally with statistics. It can often be confusing. And the difficulty with decision making based on statistics is that we never truly know what the actual state of affairs is with regard to the treatment effect. Does the treatment effect work? We want to know. And we ultimately never know the real true state of affairs, and we have to be comfortable with that ambiguity. The one thing that we have at our disposal is the data that we collect in our sample, and based on the data we make a decision. And so over here on this graphic in this table that I created, which every stats textbook has a similar table, although I put my own notations in here to make it easier to read, you have your decision. Sorry about having the cursor suddenly turn into a bar here, but I try to move around the arrow. So you have your decision based on the data, and if your test statistic reaches the critical region of the probability curve, then we reject the null hypothesis and we conclude that there is a treatment effect. But we have to be cognizant of the fact that our decision could be wrong, and we'll never know whether it's wrong or not. I mean, other people may, if we have sufficient other data from other experimenters to the point where we have perhaps hundreds of experiments and they all support the efficacy of the treatment, then we could be satisfied that the treatment really does work. So, to be clear, I'm not saying that we never know whether, for example, a drug is effective or not. Based on repeated tests, then we get to the point where we're satisfied that we have the true state of affairs within our knowledge base. And that's, of course, what drug testing is all about. So as I record this, there's quite a bit of discussion about the coronavirus. It's March 20th as I'm recording this. And there's a lot of need or a lot of worry or concern about having a treatment that's effective. One potential treatment is the anti-malaria pill. It's an antiviral. That's not a vaccine. It might treat symptoms or slow down the progression of the disease if a person has it. And the doctors are, they're conservative in terms of their approach to saying whether or not it can work, because we need to have lots of different tests to see. We don't want to administer it to millions of people until we know whether it can work. Otherwise it's giving false hope, etc. So, at the point where we have dozens or perhaps hundreds of experiments that all support the efficacy of a treatment, they've all rejected the null hypothesis in the same direction, that people who took the drug got better, then we could be satisfied that we know what the true state of affairs is. But on any single experiment, the risk is there that we have a type 1 error. So if we reject the null hypothesis, we have exactly a 5% chance that the data represent a type 1 error. And that 5% is based on the probability curve, where we set the critical region based on the 5% of the curve that we will accept to be a significant result. So that's a false positive, and it happens. It happens with some regularity, and it's hard to track these things. But when you have an experiment that shows a surprising result, and other experiments fail to replicate that surprising result, then it's an indication that we probably have a type 1 error, although there's no way to assign an actual probability to saying that it is a type 1 error, that the first result that was positive, that where we rejected the null hypothesis, there's no way to actually get a probability statement in terms of how likely that particular result is a false positive. Now, if the true state of affairs is that the null hypothesis is false, in other words, the treatment does work, then, and if our decision is to reject the null hypothesis, then we will have made a correct decision. And the probability of this happening is 1 minus beta, which is the power of the test. Now, I was not able in the last round of class to talk at length about power, so let me say something about that here. Power of the test is directly related to sample size. The more people that you have, the better power you have. You can think of power as your ability to see something if it's there. If you're looking for, let's say, if you're on the street and you drop your key and there's not much light, then you're looking for the key in a situation of low power. So power is the magnitude of light. However, if you drop your key and it's broad daylight, it's very easy to find. If you drop your key in a dark alley, and God forbid it's a dark alley in New York City in the 1980s, because you're going to get mugged. But in that situation, you're operating under conditions of low power. And so increasing the sample size is like turning up the light. It gives you a better ability to see the thing that you're trying to find. And if it's an experiment, then the thing that you're trying to find is that the treatment worked. So your ability to reject the null hypothesis is directly dependent on sample size. It's also dependent on the magnitude of the treatment. So significance is a product of the effect size. The magnitude of the treatment is the effect size, and the sample size. If you have a drug that only works a little bit or saves a few people's lives but not most people, that's a drug that has low power, or rather I should say a small effect size, but it could still be a real effect. It's a drug that has a small effect size, but it could still save some people's lives. So to be able to see that effectiveness of that drug with small effects, you need to have a large sample. On the other hand, if you had a drug that saved almost everybody who took it, you would need only a few people to be able to statistically see that. And so that's the relationship of type 1 error and power. Alpha, which is the rate of type 1 error, and it constitutes the region of rejection in our probability curve, is known to us. It's 0.05. Beta is unknown to us. The only way to calculate beta is by running a power analysis. And in order to run a power analysis, you have to know the magnitude of the treatment effect, which if you knew that, you probably wouldn't be doing the experiment. So most of the time people do experiments without knowing what beta is in terms of a numerical value. Now going down here, we see that the other option in our decision making is that we accept the null hypothesis. If we accept the null hypothesis when in fact the null hypothesis is true, then we will have made a correct decision, and the probability of this is 1 minus alpha. In other words, 95%. On the other hand, that 95% is predicated on having a zero treatment effect. So if in fact you have zero treatment effect, then 95% of the time your test results will come up non-significant. So that's what this represents, this 1 minus alpha. That if in fact the true treatment effect is 0 for the population, and we do an experiment on that treatment effect, 95% of the time we're going to come up with nothing. We're going to come up with a non-significant result. But 5% of the time, just by accident, it'll come up positive. And so that's type 1 error. So now, if we accept the null hypothesis when, in fact, the treatment really does work, what does that entail? Well, that's a type 2 error, and that's blindness to a real effect. It's a false negative. And the probability of that is equal to beta. But again, we don't know what beta is. The only way to know beta is to run a power analysis. And so in both of these situations, if we reject the null hypothesis or if we accept the null hypothesis, we don't know if we are correct. And it's a problem, because what happens is that people who find unusual things, really surprising results, those surprising results get published because they are surprising. Maybe it's really good news, or maybe it's really bad news. And so the journals that publish scientific articles like to have unusual results because they potentially move the field forward in terms of knowledge. But the downside of that is that it's also the case that these surprising results can be type 1 errors. Unless you are able to replicate that surprising result, we should not be satisfied that it is real, that it actually constitutes evidence of something like a treatment effect being efficacious within the entire population. So you can see down here that I've noted that this is a terrible system. We know the flaws in the system, and yet we still have to use it. And there's been a tremendous controversy in recent years, going back now about 10 years, as researchers conduct replications of prior experiments. There's been a notable lack of ability to replicate some of these findings, some of these well-known publications. And so that, it's called the replication controversy or replication problem. And Brian Nosek and other researchers like him, he's a social psychologist, have found that quite a large number of published studies, when they tried to replicate them, they come up with non-significant results. And that's probably evidence of publication bias, where false positives are likely to get published because they are surprising results. But it's something that we're aware of, but the field has not really come to terms with it yet. It's just something that that we have to deal with. And you see I've got a typo here, emails. I've got to go back and fix that. So here's the probability table for a T, the independent samples t-testing. You see the degrees of freedom down here. I guess I'll end on this point. This is where you find the critical value. I think most of the students are comfortable with this at this point. If you had 12 people, I guess I better go to the meeting. If you had 12 people, your degrees of freedom would be 10, and that's because you lose 1 degree of freedom in each group. And you can see that here. In this case, I've got 10 people. My degrees of freedom will be 8. And the reason why is because this number has to be 0. The deviation scores for the emails has to be 0. And the first score can be anything, the second score can be anything, the third and fourth scores can be anything. But this fifth score, this fifth deviation score, has to be the number that makes them all add up to 0. And that's why we lose that particular value as a degree of freedom. So this first group, the group of females, has 4 degrees of freedom, and the second group has 4 degrees of freedom. And so in this case, for this particular experiment, this hypothetical, we have 8 degrees of freedom. The critical value would be 2.306. Based on 0.05 two-tailed test, 0.05 alpha two-tailed test. Okay, so I think I will end this particular video here. That's a nice recap of the null hypothesis significance testing dilemma that we are in as a field. And watch for future videos talking about different things related to ANOVA and so forth. Thank you, and goodbye.